Chonghua Guo, founder of Chonghua Academy. I will teach you the primer of probability. Now we start video class 1, the two kinds of principle of counting, addition-based and multiplication-based. First, look at this example. There are 5 math books, 6 biology books on the upper and under layer of Jack's bookshelf, respectively. Math books on the upper layer, bio books on the under layer. Question 1. How many ways are there for Jack to select one book among them? Question 2. How many ways are there for Jack to select one math book and one biology book? First and foremost, let's focus on what Jack wants to do. For question 1, Jack just wants to pick one book, no matter what it is, maybe for relax, maybe for fun, whatever. Jack may happen to stare at his math books at first and easily find that if he chooses any one of them, there are totally 5 choices. 5 choices. Then he moves his eyes to the bio books and finds he has 6 choices over there. Bio books right here, and he has 6 choices right here. Each choice can independently meet his primary job requirement to pick one book. Hence, together, he has 5 plus 6 equal to 11 different ways to pick one book. Let's turn to question 2. What's different here? This time, job cannot be finished in one step, as in question 1. Jack wants to pick a math book and a bio book. Suppose we label the math books as M1, M2 until M5. We label the bio book as B1, B2 until B6. Based on the job to be done, we pair them like this. As you can see, there's different pairs right here, and we have start M1, B1, which means that mathematics book 1 and bio book 1 until M5, B6, which means that math book 5 and bio book 6. We can count all the pairs, which result in together 30 methods to pick one math book and one bio book. Another way to calculate the total is to count the column and the row. Count the column 1, 2, 3, 4, 5. So column 5 in column. 1, 2, 3, 4, 5, 6. So 6 in row. Totally 5 times 6 equals to 30 methods, the same as before. Anything interesting for this example? Yes, we notice that very interesting thing right here, and we have addition rule here, and we have the multiplication rule here. What's your observation so far? Observation 1. Solution for question 1. Elicits the definition of addition-based principle of counting. Suppose that there are 2 types of options to finish a one-step job. Type 1 consists of m different methods. Type 2 consists of n different methods. Then together there are m plus n possible methods of the two types of options. What are the key points we need our attention in particular in this definition? First, define whether the job to be done is a one-step job or not. So keyword one-step job. If yes, we can conclude that addition rule should apply. Addition rule should apply. Thus lead to second, if the problem is addition based, then identify types of options to get job done. Identify types of options, very important. And third, to double check if any single method included in each type can be used to get job done independently. So no matter whether it's type 1 from type 1 method or method from type 2, each can be used to get job done independently. If yes, then perform the addition calculation. Let's look at another example. Terry plans for a summer vacation from city A to city B, either by train or by bus. There are 3 trains per day and 2 buses per day. How many ways from city A to city B are there per day? What's the key information you can learn from the problem statement? First, we ask ourselves, what's the job to be done? Is it easy for us to find that it's a one-step job? Yes. The job to be done is to choose one single vehicle. No matter whether it's train or bus. So to choose one single vehicle available to go from city A to city B. Based on this, we can conclude that addition rule should apply. And we need to identify types here. So second, is it hard for us to classify the types? Obvious not. There are 2 types of transportation vehicles. One is train, another one is bus. Like train, this is train, and this is bus. Third, can we double check here whether it's addition based problem? Yes, we can verify that by saying that each train or bus per day can help move Terry from A to B independently. Accordingly, we can do the addition calculation, which is 3 plus 2 equals to 5 different ways. Now, let's turn to the generalization of the principle of counting. When there are more than 2 types of options to finish a one-step job, the addition-based principle of counting can be generalized. Generalization. Suppose that there are n types of options to finish a one-step job. Type 1 consists of m1 different methods, type 2 consists of m2 different methods, until type n consists of mn different methods. Then together there are m1 plus m2 plus until mn possible methods of n types of options. It can be well illustrated by the following flowchart. Given the problem statement A, there are n types of options, among which consist of m1, m2 until mn different methods. Each can get the required job done independently. That results in totally m1 plus m2 plus until mn possible methods. Let's look at example 1.2. Helen wants to select one elective course from the spring catalog. there are 5 computer courses, 2 history courses, 7 math courses, and 4 writing courses. How many ways for her to select one course among all? First and foremost, let's do some analysis. Is this a one-step job for Helen? Yes. Helen just wants to pick one course no matter what it is, that's all. Second, can we categorize the type of courses? Yes, there are 4 types of courses. Type 1 here, type 2, type 3, and type 4. Third, can we double check if each course meets Helen's requirement independently? Yes, Helen can just pick one book from either of these books. So finally, we do the addition calculation like this. Together they are 5 plus 2 plus 7 plus 4 equals to 18 different ways for Helen to select one course among all. Let's turn back to observation 2. Solution for question 2 of the starting Jack's bookshelf problem. As you remember, elicits the definition of multiplication-based principle of counting. Suppose that 2 steps are to be performed to finish a job. Step 1 consists of m different methods, step 2 consists of n different methods. Then together there are m times n possible methods. What are the key points we should focus on here? Well, first, check if more than one step need to be performed to finish the job. So we have 2 steps are to be performed to finish the job. If yes, we can conclude that multiplication rule should apply. Multiplication rule should apply. Lastly, to the second, identify the steps need to be performed. And we have step 1, step 2. Third, double check if all steps are necessary and sufficient to finish the desired job. If yes, then perform the multiplication calculation. Let's look at another example. Example 2.1. Generate a 2-digit number with number 1, 2, 3, and 4. Question 1. If the repeated number is allowed, and how many ways are there for the 2-digit number generation? Number 2. If the repeated number is not allowed, how many ways are there then? How can we address this problem? Now we write AB. AB to stand for the desired 2-digit number. B is the single digit, A is the 10-digit. Is it easy enough for us to find it's a 2-step job? Yes, of course. We determine the single digit firstly and determine the 10-digit secondly. Thus we can conclude that multiplication rule should apply here. For question 1, step 1 of selecting single digit consists of 4 methods, and step 2 of selecting 10-digit consists of another 4 methods, because 1, 2, 3, 4 is allowed to repeat. If any step is cancelled, will the required job be finished? Obviously not. So we can do the multiplication calculation. Together there are 4 by 4 equals to 16 different ways. For question 2, step 1 of selecting single digit still consists of 4 methods. But step 2 of selecting 10 digit only consists of 3 methods, because 1, 2, 3, 4 is not allowed to repeat. Once again, can we double check that if any step is cancelled, will the required job be finished? Obviously not. So we can do the multiplication calculation. Together, there are 4 times 3 equals to 12 different ways. Again, when there are more than 2 steps to finish jobs, the multiplication-based principle of counting can also be generalized. Suppose that n steps are to be performed to finish a job. Step 1 consists of m1 different methods, step 2 consists of m2 different methods, until step n consists of mn different methods. Then together, there are m1 times m2 times until mn possible methods. This generalization can also be well illustrated by the following flowchart. Given the problem statement A, there are n steps with each of which consists of m1, m2 until mn methods, m1 until mn methods, and finally gets the final destination is C. All steps need to be performed to get the required job done. That results in totally m1 times m2 times until mn possible methods. Let's look at example 2.2. How many 4-digit numbers can be made up of the 10 numbers from 0 to 9? First and foremost, let's do some analysis. Is this a multi-step job? Yes. To make up of a 4-digit number is a 4-step job. So we write a 4-digit number like A, B, C, D. A is the 1000 digit, B is the 100 digit, C is the 10 digit, and D is the single digit. Hence, we can conclude that multiplication rule should apply. Second, can we identify how many numbers exist for each step? Yes. For A, there are 9 numbers for 1000 digit because it cannot be 0. So it's 9 numbers. For 100 digit B, there are 10 numbers. For 10 digit C, 10 possible numbers. And for single digit D, 10 possible numbers. Can we double check if all steps are necessary and sufficient to finish the required job? Yes, once we determine A, B, C, and D, and we can get the 4-digit number. So finally, we do the multiplication calculation like this. Together, there are 9 times 10 times 10 times 10 equal to 9 times 10 cubed. Different ways to make up of 4-digit numbers. As the last part of video class 1, we leave some assignment for you to practice. You are encouraged to address them before you watch the next video, where we will share some possible solutions for them. This ends our video class 1.